look at how a couple of ideas from number theory can be used to solve like competition style math problems. Now, number theory is a huge subject, and it would take hours and hours and hours to cover everything. And in fact, I've got a whole playlist where I do just that. I taught a course on number theory at the college that I teach at, and I made videos for every day of the class. So you can check that playlist out if you want. Also, my playlist where we look at competition math problems, it's called the Math Contest Problems playlist. It has a lot of number theory problems as well. So in the end, there's a ton of number theory stuff on this channel if you guys are psyched. So first, we're going to look at some basic definitions and basic results, and then do two examples. So as far as basic definitions, the first one is divisibility. So we say that A divides B, or sometimes B is divisible by A, if B equals A times N for some natural number N. So in other words, B is a multiple of N. Okay. Next, we say that D is equal to the GCD of A and B if D divides A, D divides B, and it's the biggest one that divides both, but how do we order this largest idea? And we do it by divisibility. So if C divides A and B, then C divides D. So that means that C is smaller than D because it divides it. Okay, next we say that P is prime if, when we have a divisor of P, that divisor is either 1 or the prime itself. And I should point out that we do not take 1 to be a prime number. 1 is a unit, and kind of in the theory of like algebraic number theory, units are not allowed to be primes. Okay. Next, we have this idea of congruence modulo n. So we say A is congruent to B mod n, and we write it like that, if n divides A minus B. So this is a little bit trickier, so I've got some examples. So notice 12 is congruent to 3 mod 9, because 12 minus 3 is divisible by 9. 15 is congruent to 2 mod 13, because 15 minus 2 is divisible by 13. And finally, 33 is congruent to 1 mod 4, because 33 minus 1 is 32, but that's 4 times 8. So notice when you're working with congruence as mod n, you only really need to think about n total numbers. 0, 1, 2, all the way up to n minus 1. Because essentially what you do when you reduce modulo 9, 13, or 4 is you divide and keep the remainder. So that's another way of thinking about this. So notice 12 divided by 9 is going to be 1. Keep the remainder, that's 3. 15 divided by 13 is 1, remainder 2. 33 divided by 4 is 8, remainder 1. So this idea of congruence is equivalent to the idea of having the same remainder after being divided by n. Okay, let's look at some standard results that show up in these math contest type problems. So the first one is Bézout's lemma, sometimes called Bézout's identity. And this is not exactly that identity, but a powerful result that follows from that identity. So we have for all natural numbers A and B, this linear Diophantine equation, that's what this is called, ax plus by equals n, has a solution with x and y in the integers if and only if the GCD of A and B divides n. So this immediately allows us to figure out if one of these has a solution or not. It doesn't tell you the solution, but it tells you that there is a solution. Like, for instance, if we have 3x plus 9y equals, let's say, maybe 25, we can see that that does not have a solution because the GCD of 3 and 9 is equal to 3. 3 does not divide 25. So we have no possible way to get a solution out of that. Then maybe the next question is, how do you find a solution? Well, that has a process of its own called the extended Euclidean algorithm. So I've got some videos on the extended Euclidean algorithm if you guys are psyched about that as well. In fact, if someone wants to make a list of a lot of links to these videos, I'll pin it to the top of the comments if you guys want. Okay, so next we have this thing called Fermat's little theorem, and that says if p is prime and p does not divide a, then a to the p minus 1 is congruent to 1 mod p. And so I've got a little example cooked up for this. So this Fermat's little theorem says that 5 to the 6 mod 7 should be the same thing as 1 mod 7. Let's just go ahead and check that. And we'll check that by successively multiplying by 5. So we've got 5, and then the next thing is 5 squared, which is equal to 25. But we might as well reduce mod 7 because we don't really need to worry about numbers that are bigger than 6. So let's see, if we reduce this thing mod 7, we'll get 4, because it's 4 more than 21. Now let's go ahead and multiply by 5 one more time. So that's going to give us 5 cubed, but that's also 5 times 4, which is 20. But notice 20 is the same thing as negative 1 mod 7. But now if 5 cubed is negative 1 mod 7, then that means 5 to the 6th is the same thing as 5 cubed squared, which is the same thing as negative 1 squared, which is clearly 1 mod 7. So notice there are lots of types of tricks for reducing mod n. Okay, and then the next thing that I want to talk about is this fact that only certain numbers, and these really should be residues, are perfect squares or perfect cubes, etc., mod n. So I'm going to cook up an example for this too. Let's work mod 9, which means we only need to look at the numbers 0, 1, 2, 3, 4, 5, 6, 7, and 8. So what I want to do is square each of those numbers and see what the output is mod 9. So if I square 0, I'll get 0. If I square 1, I'll get 1. If I square 2, I will get 4. If I square 3, I will get 9, but 9 is equal to 0 mod 9, so I've got 0. Next, if I square 4, I will get 16, but notice 16 is equal to 7 mod 9. If I square 5, I'll get 25, but notice 25 is also 7 mod 9. If I square 6, I'll get 36, but notice 36 is 0 mod 9. If I square 7, I'll get 49, but let's see. 49 is 4 mod 9. And then if I square 8, I'll get 64, but that's going to be 1 mod 9. So notice we only have a certain number of perfect squares mod 9. We have 0, 1, 4, and 7. So that means it's impossible to square a number and get something that's congruent to, say, 2 mod 9, or 3 mod 9, or 5 mod 9, or 6 or 8 mod 9. So there are only those possibilities. Okay, I'm going to go ahead and get this cleaned up, and we're going to look at 2 examples. So our first example comes from the AIM, and the year is 1985. So we want to consider the sequence of numbers a sub n, and it's defined by 100 plus n squared. And then another sequence defined on top of that, d sub n, which is the GCD of a sub n and a sub n plus 1. And our goal is to find the maximum of this sequence d sub n. Now, let's go ahead and jump into the solution. So I would say your first thing that you should do is explore. And when you explore with small values of n, what you will find is that the GCD seems to be 1 most of the time. So for small n, the GCD of an and an plus 1 is 1, and I'll put here mostly. So that obviously doesn't prove that it's 1 all of the time, but it says that we need to try a little bit harder to find a place where it is not equal to 1. And so the way that we'll do that is cook up a value of a sub n and a sub n plus 1, or really a value of n, that will find some larger greatest common divisor between those 2 values of the sequence. So there's 2 ways you can approach this. You can look at the case when n is even and then n plus 1 is odd, or when n is odd and n plus 1 is even. And I think both will get you to the same place, but we're going to look at the setup when n is even. So let's go ahead and suppose that n equals 2k for some k, which is a natural number. And let's look what a sub 2k, or a sub n in this case, looks like. So that's going to look like 100 plus 4k squared. Great. And then let's look at what a sub 2k plus 1, or a sub n plus 1 is in this case. So that's going to be 100 plus 2k plus 1 quantity squared, but we can multiply that out pretty easily. That's going to be 100 plus 4k squared plus 4k plus 1. Okay, so the thing that we want to do is tweak our value of k so that we can factor each of these objects in a way so that we have a common factor between them, and a common factor that's obviously the greatest common factor. So let's go ahead and look at this for a little bit and see what might work. So notice if we set k equal to 100 up in this one, well, we can factor it pretty nicely. So this is going to turn into 100 plus 4 times 100 squared. I'm going to write it like that so it's obvious how to factor this. Now we can factor that as 100 times 400 plus 1. So that's what we do if we factor the 100 out. So now let's likewise see what happens if we plug k equals 100 into this thing down here. So I'm going to plug it into this part, so that gives me 100 plus 4 times 100 squared plus 4 times 100 plus 1. So now in order for this thing to have a nice common factor with our a sub 2k, which is that thing up there, maybe we want to factor something like 4 plus 100 out of there. Let's see how we can do that. Well, notice that we can take this 100 and add it to this 4 times 100, and then visualize this as 4 times 100 squared, so that's like that term, plus 5 times 100 plus 1. Now we're looking at that like a quadratic polynomial where the variable is 100, and we can see that that is going to factor like 4 plus 100 and then 100 plus 1. Good. So the next thing to notice is that 100 plus 1 and 100 are relatively prime. That is, they share no common divisors, which makes this 401 in fact the greatest common divisor of these two. So notice what we have here, the GCD of a sub, I'm going to write 200, comma, a sub 201 equals 401. So we had to work pretty hard by guessing a really nice value of k in order for this to work out. So it's a reasonable claim that this is the maximum of all of the greatest common divisors. So I'll go ahead and clean up this board, and that's what we will prove. So in the last board, we made some careful guesses to come up with this fact that the GCD of a sub 200 and a sub 201 is equal to 401. And putting this in the language of our D, this is D sub 200. So we have D sub 200 is 401. And then we, motivated by the specialness of our choices here, that this is probably the maximum of all of these dn's. In other words, the maximum of dn as n ranges over all natural numbers is 401. And that's the claim which we are now going to prove. And we'll prove that by showing that we have this like linear Diophantine equation with two values of this sequence that add up to 401. In other words, we want to solve a sub n times x plus a sub n plus 1 times y equals 401 with x and y in the integers. And then by that result that's related to Bézou's identity, what that will tell us is that the GCD of an plus 1 is going to divide 401. But if a number divides 401, then it's going to be less than or equal to 401. Okay, so now let's get to solving this equation. So like I said before, the standard way to do this, if you've got a handle on the numbers, is the extended Euclidean algorithm. But we don't have a handle on the numbers here because we're going to have this n floating around in all of the equations. So we're going to have to do a little bit of guess and check and a little bit of reasoning. So let's see what this equation turns into when we plug in a sub n. So we're going to have 100 plus n squared times x plus 100 plus n plus 1 quantity squared times y equals 401. So that's a rewritten version of the equation that we want to solve. So let's go ahead and maybe multiply this out, and notice we're going to get 100 plus n squared plus 2n plus 1, like that. The next thing that I want to do is take this left-hand side of the equation and rewrite it where I've combined all of the numbers together, all of the coefficients of n together, and all of the coefficients of n squared together. So let's see how we can do that. So all of the numbers will be 100x plus 101y. So let's see how we get that. We get 100 times x, and then 100 plus 1 times y. So that's good. And then next, for the coefficients of n, let's see what we have. So in this case, we don't actually have that much. We have 2n times y. So I'm just going to write this as n times 2y, like that. Now let's look at the coefficient of n squared. So we've got one here that's being multiplied by x, and then one here that's being multiplied by y. So n squared times x plus y. And this needs to be equal to 401. So we're not going to be able to just pull out some number x and number y like 37 and 55, because that's not going to cancel this n where n is arbitrary. So what we need is to pick x and y that depend on n. So let's maybe see how we can do that. Another thing to notice is that we want x and y to depend on n, but I think they need to linearly depend on n so we don't continually scale up the exponent of n that's over here on the left-hand side. So maybe we'll set x equal to r plus sn, like that. And then we'll set y equal to t plus something times n, but we can actually decide what this coefficient needs to be immediately. And that's because there's no n cubed term on the right-hand side of the equation. So when you multiply n squared with x, you're going to pick up an n cubed term that must cancel. So in other words, the coefficients of n in x and y must be equal and opposite. Okay, so now let's go ahead and shove this version of x and y up into our original equation and see what we get. So we're going to get 100 r plus sn plus 101 t minus sn, like that. And then we're going to have plus 2 times n times y, which is t minus sn. And then we've got x plus y, but that's going to be r plus t times n squared. So we've got n squared r plus t. So that's going to equal 401. So now we're going to do the same thing that we did before, where we put all of this together with the numbers, the coefficients of n, and the coefficients of n squared. So let's see what the numbers are in this case. So we're going to have 100r and then 101t. So that's going to be 100r plus 101t. So that gets us started. Those are our numbers. Now let's see what the coefficients of n are. So we've got plus n times, so we've got 100 times s from this term, minus 101 times s from that term. So that gives us, in the end, a negative s. And then over here, we've got plus 2 times t, like that. Good. And then, what do we have for n squared? Well, let's see what we have. We're going to have n squared r plus t, so that comes from this bit right here. And then next, we're going to have minus 2 s, and that comes from this term right here. So that 2n times the minus sn. And we want all of this to be equal to 401. Okay, so I'll maybe go ahead and bring that up, and then we're pretty close. So on the last board, we argued our way to the following equation. So first we had this setup where we set x equal to r plus sn and y equal to r minus sn. Then we got this thing 100r plus 101t plus n times 2t minus s plus n squared times r plus t minus 2s. And all of that needs to be equal to 401. Now notice the left-hand side is a quadratic polynomial in the variable n. Notice n can be varied to be anything here, but the right-hand side is just a constant. So this type of equation needs to hold for all n. So that means that the coefficient of n here must be equal to 0, because there's no n on the other side of the equation. And the coefficient of n squared here also has to be equal to 0, because likewise there's no n squared on the other side of the equation. And then finally, this guy right here needs to be 401, because that is all we have on the other side of the equation. So that gives us this system of equations, 100r plus 101t equals 401, and then we've got 2t minus s equals 0, and then r plus t minus 2s equals 0. So let's see if we can put all of this together to solve for r, s, and t. So notice this thing immediately tells us that s equals 2t, just moving the s over. Now we can go ahead and take this value of s and plug it in here, and that's going to give us r plus t minus 4t equals 0. So let's see, that means that r is equal to 3t. Because we've got t minus 4t is negative 3t, move that over, we've got r equals 3t. So let's see, we can plug this value of r in here, and that's going to give us 300t plus 101t equals 401. But that means 401t equals 401, which means that t equals 1. Great. But now if t equals 1, that means that s equals 2. That's what we got there. And then finally, that means that r equals 3. Good. So that means our solution looks like this. So we have a sub n times r plus sn, so that's going to be 3 plus 2n. And then we've got a sub n plus 1 times y, which is t minus sn, so that's going to be 1 minus 2n, so that's going to equal 401. So we found the linear combination of an and an plus 1 that's equal to 401. But that means that the GCD of an and an plus 1 must divide 401. That makes 401 the greatest possible value of d sub n, but we found a place where d sub n was exactly equal to 401, so we achieved that largest possible value. And so that finishes this problem. I'll go ahead and clean this up and we'll look at one more. So for our last example, we're going to look at a classic problem. And that is to show that there are infinitely many positive integers that cannot be expressed as the sum of 3 cubes. So the easiest way to do this is to work modulo something and look at all of the cubes modulo that number and show that there are some residues modulo that number that are unachievable by adding any 3 of the cubes. And really, how do you figure out what that number is? Well, you just kind of have to play with it until you find one. So I'll just jump right to it. We're going to work mod 9. So let's work mod 9. And we're just going to look at a chart of numbers. So I'm going to have this chart n, and then I'll have n squared mod 9, and then I'll have n cubed mod 9. So obviously you don't really need n squared there, but I'm just going to put it there so we have got a two-step calculation going on. Okay, so now let's go ahead and start this chart. So 0, 0 squared is 0, 0 cubed is 0, that's easy. So 1, 1 cubed is 1, 1 squared is 1, and then 1 cubed is 1, so that's not too hard either. So now 2 squared is 4, 2 cubed is 8. Well, that's not too bad either. Now let's look at the next one. 3 squared is 9. Well, that's already equal to 0, which means that 3 cubed is also equal to 0. Now let's look at 4. So 4 squared is 16, but notice 16 is equal to 7. Now we take 4 cubed, which is going to be 4 squared times 4. In other words, it's going to be 7 times 4. Well, that's going to be 28, but 28 is 1 more than 27, so that's going to be 1. Good. And then actually, this pattern repeats. And it's actually pretty easy to show that this pattern repeats without doing the calculation. I'll let you guys think about that. But I'll just do the last couple. So 5, 6, 7, 8. So if we take 5 and we square it, we get 25. And so notice that 25 is 7 mod 9. And then 5 times 7, which is going to be 5 times 5 squared, is 5 cubed, but that's going to be 35. But 35 is 1 less than 36. That makes it -1 mod 9 or 8 mod 9. So now let's look at let's look at 6. 6 times 6 is 36, which is already 0, so we get a 0 here. And then suffice it to say, this thing is just going to repeat one more time. So we're going to have a 0, a 1, and an 8. So now we only have as tools the numbers 0, 1, and 8. And I'll say that it is impossible to achieve the numbers 4 or 5 using only 0, 1, and 8 if you're working mod 9. So we can actually write this a little bit more carefully by saying that if x, y, and z come from the set 0, 1, or 8, then x plus y plus z congruent to 4 or 5 mod 9 has no solution. But what that tells us is that any natural number that is congruent to 4 or 5 mod 9 cannot be expressed as the sum of 3 cubes. So we can finish that off by saying So we can conclude this by saying that 9k plus 4 and 9k plus 5 for all natural numbers k cannot be expressed as the sum of 3 cubes. Because if we could express a number of that form as a sum of 3 cubes, then we would have a solution to this up here, but we can show that there's no solution to that up there just by brute force looking at our calculations here. And that's a good place to stop.